which says, so let ui, these are just set theoretical exercises. Okay, if you know the definition of an open set, and if you know set theory, then you can answer these questions. So let ui, u1, u2, un be a finite collection, be a finite collection of open sets of open sets in a matrix space, xt, then show that that intersection, this finite intersection, okay, this finite intersection of ui where I runs from 1 to n is open in X, is open in X. So what does this say? It says that arbitrary union of open set is open, but the finite intersection of open set is again open, right? So it says finite intersection of open sets is again open. What about infinite intersection? Right? So the question that you can ask here, what about finite union? Whether the finite union of open set is again finite, and here you can ask about whether the arbitrary intersection of open set is again open or not. Such questions you can ask yourself and you can try to answer them. Okay, so this is your second homework. Okay. Okay, now this is also a very easy exercise. It's not really that difficult. Okay, so before I want to give you the definition of a topology. So let me give a definition of topology. Very important definition of topology. Okay, it says let X be a non-empty set. Let X be a non-empty set. Assume that we are given. Assume that we are given a collection tau. We are given a collection tau of subsets of X, satisfying now there are three properties. The first property, it says that the empty set and X itself, phi and X, they are in this collection tau. Okay, they are in this collection tau. Second property, it says now you take arbitrary elements from, okay, let me write down arbitrary union of members of tau again lies in tau. What does this mean? It means you have take any number of elements from tau. That collection may be finite, it may be infinite, it may be countable, it may be uncountable. Okay, take any number of elements from tau, and if you look at the union of all these elements, the such a union again must belong to tau. Okay, and the last one, it says the intersection of any finite number of intersection of any finite number of members of tau my tau, you know, sometimes it looks different, but it's tau. Okay, the intersection of any finite number of members of tau lies again in tau. It lies again in tau. Okay, it lies again in tau. So tau is called, then such a collection tau is called there can be more than one topology. Okay, it can called topology on X. It is called a topology on X, and we denote it by, this is the notation for a topological space. X with this collection is known as topological space. This is a topological space. Okay, please read the definition. Okay, can any person give me example of a topological space? Look at your homework. Your homework says that if XD is a metric space, then arbitrary union of open sets is again open. And the second homework says that the finite intersection of open set is again open. And if you compare this with the definition of topology, then the second property of the topology, this corresponds to your first homework. And the third condition or the third property of a topological space, it corresponds to your second homework. Right? And we know that both phi and x, they are open. They are vacuously open. Phi and x are open. Now, can somebody tell me, can somebody give me example of a topological space? It's there in front of you. So for example, let XD be a metric space, and what should be my tau? Tau is the collection of subsets of X such that U is open in D, right? Or U is an open set in D. U is an open set. That's all. So then by your homework, this pair x tau, this pair x tau is a topological space. Is a topological space. Okay, any doubt, any question? The keywords are these two: arbitrary union and finite intersection. Finite intersection. These are two keywords. So this is a definition of a topological space. Now let's do a few more examples. Okay, last time we have defined what are equivalent matrix, right? So we say two matrix D and D dash on a set X are equivalent if and only if U is D open, if and only if U is D dash open, right? So this is one definition of equivalent metric, and there is another definition of equivalent metric. Okay, so this is another definition. Another definition of equivalent matrix. Equivalent matrix. So we say that two matrix. We say that two matrix D and okay. Now you people don't know what is a topology generated by. That is what you people don't know. Okay, let me just write down this definition. We say that two matrix D and D dash are equivalent if and only if the topology generated by okay D dash are on a set X are equivalent if the topologies generated by D and D dash are the same. D and D dash are the same. Now what is the topology generated by D? Right? We haven't discussed that thing. Okay, again it's there on the board. Can anybody would like to shed some light on what is meant by topology generated by a metric? My handwriting is very worst. This is one of the few things which I have always wanted to work on, but never. So note, okay, here I'm adding the note, okay. Note the above topology tau is said to be generated by the metric which metric was here? D, by the metric D, right? So we are given a metric space X with the metric function D, and what we are doing, we are just looking at the collection of all the open sets. Such a collection of all the open set, it forms a topological space, and such a topological space is said to be generated by the metric D. Okay. Now this definition makes sense. This definition, it makes sense. Any question? So we have seen a lot many metrics, right? Now, can somebody give me that Venn diagram? Do you recall that Venn diagram of which we have mentioned it few times? Okay. Few students, they have provided examples also. For example, Prerna, she had given me example of a metric which is not coming from norm. बरोबर आहे ना? असंच काहीतरी something she had. So this is the connection. Yeah, बराबर है ना? वही था ना?
हाँ sir, discrete matrix space.
Discrete metric, yeah. So the collection of inner product space, it sits inside the collection of norm spaces. The collection of norm spaces, every norms gives us a metric. It sits inside metric spaces. And every metric space, now we have just seen, every metric space gives us a topology. So this is your topological space. Or topology, just topology or topological space. So this is the diagram of the inclusion of spaces. Okay. So being an inner product space is very strong. This is very strong. When you have some space which is endowed with some inner product, then it is very strong, very nice person. Okay, nicest or the most nice, I don't know, the most nice person that you can encounter, right? And topology is like just any other lame person. Okay. Yeah. Okay. Any question? So this is inclusion. It should be with you. I will keep it here. I'll just minimize this one. So topology means surface. Okay. Topological spaces, they speak about the properties of surface. Surface doesn't make sense all the time, right? So it speaks about the properties of surface of some space. Okay. Yeah. You can see topology. Topology means study of surfaces. Okay, now we are going to do one more exercise, and then I will leave one homework for you people. I will be doing one generalized exercise, and okay. So this one is a little big one. So be attentive. Okay, we say that. Before that, let me give one definition. Definition. So we have defined what are two equivalent metrics. The next thing is to define what are two equivalent norms. Okay, so we say that two norms. We say that two norms, norm 1 and norm 2. We say that two norms, norm 1 and norm 2 on a vector space V, on a vector space V are equivalent if the matrix induced by them if the metrics induced by them are equivalent. Right? If the metrics induced by them are equivalent, and we know when two metrics are equivalent, right? Okay. Okay, let's do one exercise, then we'll move to next topic. Any question? So here also you can see every norm gives us a metric, right? So these norms, they also gives us metrics. These metrics are called as induced metrics. Okay, no question? Okay, now let's do this homework. So it says, show that the norms norm 1 and norm 2, norm 1 and norm 2 are equivalent Now this is if and only if statement. If and only if there exists positive constant, there exists positive constants C1 and C2 such that C1 and C2 such that C1 and C2 such that C1 times norm 1 of x is less equal norm 2 of x is less equal C2 times norm 1 of x, and this is true for all x infinity, for all x infinity. Okay, some textbook they use this criterion as the definition of equivalent matrix. Okay, so please read the statement. The weather here in Pune, it's pleasant and at the same time it is very hot. Okay, so let's prove his statement. Okay, now we'll assume that norm 1 and norm 2 are equivalent. Okay, this is our first assumption. So first assume that norm 1 and norm 2 are equivalent. Okay, If so by definition, so let's D1 and D2 be the matrix. D1 and D2 be. Let me check. There is some. Okay, so let's D1 and D2 be the matrix induced by norm 1 and norm 2 respectively. ऐकू येते का? So note that D1 and D2 are equivalent. Okay, note that D1 and D2 are equivalent. This is by definition. Note that D1 and D2 are equivalent. This is by definition. Okay. Now I want you people to help me here. Now, this is open ball in D1 centered at 0 and of radius 1. Now, D1 01 is open in norm 2 is open in norm 2 is open in norm 2 or D2. Therefore, there exists are positive such that if I draw ball around 0 of radius r in the metric D2, then this ball sits inside D1 0. Why this is true? Can somebody tell me why this is true? Why this statement is true? We have discussed one exercise yesterday. Do you recall? So if you recall,
D1 and D2 are equivalent, that's why.
D1 and D2 are equivalent. What does that mean? It means if I take any set which is open in D1, so suppose for example this D101 is open in D1, so fix any point and I must get some open ball in the other. So if you remember, I used to draw these balls which used to sit inside. So we must get some ball around any point in B101 in the metric D2. Right? Similarly, you take any ball in metric D2 and any point, say here for example 0 itself. Okay, so this was our 0 itself. Inside this ball, I must get some ball of radius r dash such that this ball, let's call this ball as b1 0 r dash. This is a ball in metric 1 and it must sits inside this ball. Then only these two metrics are equivalent, right? We have discussed this thing yesterday. Do you remember it? Sonali? Right, so we have discussed this exercise yesterday. So that exercise that guarantees that this statement is right. So since this B101 is open in norm 1 and since these two matrices D1 and D2 they are equivalent, by that exercise we get R greater than 0 such that this ball, now this ball is in metric D2, this ball sits inside the ball B101. Right? Okay. Now take a point, take a non-zero point x. So let x is not equal to 0 and we are defining y. So y is defined as rx upon 2 times norm 2 of x. 2 times norm 2 of x. Okay. Now let's compute norm 2 of y. So norm 2 of y is same as norm 2 of rx upon 2 times norm 2 of x. Now pull out all the constant. So these are constant. I is constant, 2 is constant. They are all positive constant. And similarly, norm 2 of x is also constant. So what remains is just r by 2 and this is less than r, right? That is norm 2 of y is less than r. Okay, what does that mean? So this implies y is in this ball B20R. Therefore, now this ball B20R, 0R, this ball is contained in B101. So this implies y belongs to B101. What does that imply? That implies that distance of y from 0, that is norm 1 of y, is strictly less than 1. But what is y? What is y? So this is norm 1 of what is I? Rx upon 2 times norm 2 of x is less than 1. Now pull out the constant and everything outside. What we get is r by 2 times norm 2 of x into norm 1 of x is less than 1. Right? Okay. Let me save this. Okay. You can think this, think over it, and ask me any question if you have any question. Okay. So what does this gives us? What does this gives us? So this implies r by 2 times norm 1 of x is less than is less than norm 2 of x, and set your c1 is equal to r by set your c1 is equal to r by 2, right? So see what we are doing. We are assuming that these two norms we are assuming that these two norms are equivalent, and our job is to find these constants c1 and c2 which satisfies this inequality. This is our job. So we have found c1. How to find c2? Right? We have found c1. How to find c2? Now to find c2, repeat the same argument. Similarly, this ball B201 is open in norm 1 or D1. I'm going to follow all the arguments which I have presented here onwards. Same arguments. Okay, so similarly, B201 is open in norm 1 or D2. Therefore, there exists R dash positive, right? Such that there exists R dash positive such that this ball B10 of radius R dash is contained in B201, right? Same exercise which we did yesterday. Okay, so now we are making use of this claim, right? So B201 is open. Since D1 and D2 are equivalent matrix, we can find such a ball, right? Such a ball. Okay. Let me repeat the same argument. So let's have these arguments just there. Okay. Now take any point. So let x naught equal to 0 and y is defined as rx upon 2 times norm 1 of x. Okay, then observe that I'm not going to repeat those same arguments. Then observe that norm 1 of y is less than r. Therefore, you can use arguments like this, okay? To show that norm 1 of y is less than r, just make use of arguments like this, okay? So therefore, what can we say? This y is in B1 0 r dash. Now this ball B1 0 r dash is contained in this ball, right? So this implies y belongs to B2 01. Okay, but So this is same as saying norm 2 of y is strictly less than 1. But what is your y? This is your y. So this implies norm 2 of Rx or 2 times norm 1 of x is less than 1. Now simplify this thing. Okay. Simplify these things. What they yield. So what they yield? So this is equivalent to saying, sorry, it is R dash. Okay, R dash, R dash. Now it is all correct. So this implies R dash by 2. Similarly, norm 1 of x. Here what remains is norm 2 of x is less than 1. And this is equivalent to saying norm 2 of x, norm 2 of x is less than 2 by r dash times norm 1 of x. Now what will be your C2? So set C2 is equal to 2 by r dash. This is your C1. This is your C2. Call this as alpha. Call this as beta. So what do you get from alpha and beta? हॅलो, आहे का? मी ऐकू येत आहे का? आहेत का कोण तिकडे?
हो सर.
So thus from alpha and beta we get C1 norm 1 of x is, we got the strict inequality, right? Less than norm 2 of x is less than C2 times norm 1 of x, right? Here, norm 1 of x. Okay. So if you have any question, you can ask me. Now you may think that the proof is difficult. It is not really difficult. We are just making use of definitions, not more than that. Just the definition and the exercise which we discussed yesterday, not more than that. Okay. Okay. Now what is remaining? Which part is remaining? Converse is remaining. Okay. So let's go back to the converse part. Can somebody tell me what is the hypothesis for converse part and what we want to do? Now we are going to assume the existence of such constant C1 and C2, we are going to assume the existence of such constants C1 and C2 which satisfies this inequality, and we want to prove that these two norms are equivalent. This is what we want to prove. Okay. Okay. Now let's move to that part. Are? Oh. Where is? Okay, in the meantime, let me take the attendance. 1,
Present, sir.
2, 3,
Present, sir.
4,
Present, sir.
5,
Yes, sir.
6, 7,
Yes, sir.
8,
Present, sir.
9,
Yes, sir.
12, 9, 10,
Present, sir.
11,
Sir.
12,
Present, sir.
13,
Present, sir.
14,
Yes, sir.
15,
Present, sir.
16,
Yes, sir.
17,
Present, sir.
18,
Present, sir.
19, 20,
Present, sir.
21,
Yes,
20,
sir.
23,
Yes, sir.
24,
Present, sir.
25,
Yes, sir.
26, 27, 28,
Present, sir.
Hello, sir. 27 present.
27 is present, 28,
Present, sir.
okay, 29,
Yes, sir.
okay. So conversely, let me just write down the hypothesis. There is still किती time राहिलाय? So conversely, assume that there exists. One thing is remaining. What about equality? Equality is not there. How to get the equality? Go through the proof and why that equality was missing there. Figure it out. Okay, so next assume that there exists a positive constant. Was it positive constant or non-negative constant? It was positive constant. Okay, so assume that there exist positive constants C1 and C2 such that C1 and C2 such that C1 norm 1 of x less equal norm 2 of x less equal norm C2 times norm 1 of x. What do we want? We want norm 1 and norm 2 are equivalent. Norm 1 and norm 2 are equivalent. By definition, it is equivalent to saying, by definition, this is equivalent to saying when two norms are equivalent, that is D1 and D2 are equivalent. right? Two norms are equivalent if and only if the matrix induced by them are equivalent, right? Okay, again I'm going to make use of that exercise, the exercise which we have used earlier, right? So here, so what we are going to do is, if we are given a ball around x and of radius r, so suppose this is a ball in b1x, okay, suppose this is ball in the metric space induced by the metric d1. What we want another ball, right, of radius yes, but this ball is now in the metric d2, b2xs, right? So depending upon this r, we want such s, and the same way, right? Okay, this is what we want to show, but we have shown already what is b1xr. What is b1xr? b1xr is nothing but x plus r times b101. And what is b2x? Yes, this is nothing but x times b20, s times b201, right? Right, if you remember yesterday's discussion, all these balls will be knowing, we will be having the all the information of such type of balls only if we have control over such balls, right? बराबर है ना? So what we want, so b2x yes is contained in b1xr. This is true if and only if so this is set theoretic notation. b2x is x plus s plus b2 1 is contained in x plus r times b1 01, right? And this is same as saying that this b1 0, this xs, it's not, we cannot cancel this x plus, but this is just set theoretic, okay? So this is same as saying that this ball, which ball? This is same as saying as this ball b2 centered at 0 of radius s is contained in the ball b1 centered at 0 of radius r, right? Okay, this cancellation is not because of, these are not algebraic operations, okay? X plus s b201, these are set theoretic operation. Okay, any question? Means what does it means is that if we are given such a ball, so for example, if we are given a ball b101, then our job is to find such a real number s, such that this ball b2 0s is contained in B101 and the other way also. Okay, and if we are given the ball B201, then our job is to find a real number T such that this ball B10T is contained in B201. This is our job. We don't need to consider balls like this. B1XR, B2XR, right? Because we have already shown that these balls are nothing but of this type. Okay. So let's stop here and